exclusive OR is basically us running two different gates. We have, let's say, one set of inputs, one pair, and we want them to be evaluated at the same time by an OR gate, and to make it simple, I'll say an AND gate. Okay? And we want the results of these for exclusive OR to be true. We want an OR to be 1 or true, and we also want AND, or we don't want AND to be 1. This describes the exclusive OR attribute. One is on, but not both. The reason why this is if we look at all of the possibilities, 1, 0, 0, 1, 1, 1, and 0, 0. If you remember, the easy way of figuring this out, XOR result, A, B, is, are they different, right? Are they different? Yes. Are they different? Yes. Are they different? No. Are they different? No. So that's a shorthand way of doing it. Are they different? But this is the way that we actually build that logic, right? At least one is on, which means that they're both not 0, right? But they're both not 1. And that means, of course, that we have at least one that's 1 and at least one that's 0. And we combine these together. Now, how do we combine 1 and 0 to use any kind of, with any kind of gate? Well, we would flip this. So the AND really becomes not AND. We flip it. Right? So this is a 1, right? It's the opposite of this. And then these two we put into an AND gate. I think this is getting kind of long. Actually, I really should be using these symbols since that's what they are. So let me do that. So the OR, OR comes first. He has a curved back and front. So this is OR. Is this on camera? No. Okay. And then we have an AND who has, sorry, a not AND who has a straight back, curved front, and a circle. I'm assuming these circles are just inversions because this not has a different symbol but a circle, and then all of these not and, not or, not, oh, I don't even know what this one is. Exclusive, not or, it has a circle. We can kind of walk through it and see if we can figure out what it is. Exclusive, not or. I guess it's the inverse of exclusive or. But then why not call it not exclusive or? Maybe there's some nuanced difference between an inverted exclusive or in this. But the symbol matches. It looks like an exclusive or with a circle on the front. And I'm assuming this is not. This just means not because and not and is the only difference. There's a little circle. But I don't know. Anyway, so we have a not and. So you have an or. And my pen keeps hitting the light. Not and. And then what's going to happen is the results of these are going to feed. Big curved front. Looks like a big bullet bill from Mario. Into an AND gate. And the result of which is going to be our XOR result. Let me raise this up a bit so I don't keep hitting it. Okay, so we have A and B as inputs. And we're going to use the same A and B, right? So A goes here, and A also goes here. So this is going to be like a parallel type connection. And then B goes here, and B also goes here. We put them into the AND gate, and then the output of the AND gate is our exclusive OR result. So if we do our samples, A and B, and our XOR result, then 1 and 0, 0 and 1, 1 and 1, and 0 and 0. So let's run through this. And just remember, not and, I'm going to say not and equals and that is flipped. And for programming, I would say an exclamation mark. So not and. There's probably some other symbol I don't know about besides the circle, but I'm not gonna. So we know that not and, we just do the and we flip it, right? So if we have 1, 0, that means 1 goes here and 0 goes here, or evaluates to true, right? Because 1 or 0 equals 1. And then A and B in here, 1 and 0. Well, 1 and 0 makes 0. So we flip the 0 to a 1, and this gets a 1. So we have a 1 here and a 1 here, which means that these two become a 1 result. So it's true that it's exclusive OR. 0 and 1 is the same thing. 0, 1, 0, 1. Are one of those 1? Yes, so this gets another 1. Not and. Is 0 or 1, sorry, or let's just say it's and. Is 0 and 1 equal to 1? No. It's a 0, but not and flips to a 1, so 1 and 1, we get another 1. 1 and 1, so or are 1 or 1, I guess we could say are one of them turned on, or one of them true? Yes, that's a 1. Are 1 and 1 both 1, and gets a 1, not and flips it to a 0. So we have a 1 and a 0. So this evaluates to false because 1 and 0 equals 0. And then if they're both off, OR gets a 0, right? Because nobody's on. And are 0 and 0 on? No. So and gets a 0. We flip it to a 1. So 0 and 1 make 0. So that is how that works. Maybe there's an easier way of explaining not and instead of saying do an and then flip it, but that's, in my mind, the simplest way. I hope that helps. So pretty much have to just start building this thing now. So we need an OR gate, we know that. And we need a not AND gate, we know that. And then we know that we have to combine both of them into an AND gate. So this is going to be very interesting. It's going to be 3 different gates together. Much more complex than anything I've done so far. And going to be really cool to see things working together, hopefully. So let us get rolling. This is my last one. Another spaceship. So that guy is the last one. All right, so let us get started. We know, of course, that we're going to need 2 inputs, right? I wish this was a real schematic because that'd be cool, but I'll try and get there. But we know that we need 2 inputs, and we know that they're going to have to be connected to both of these. So this guy is connected, and this guy, oh man, is connected. Sorry, it's so messy and terrible. But it's the same input, so we need an A and a B. 2 of our favorite buttons. All right, I'm gonna spread this way out because I know that just to make it simple, and then we can maybe confine it later and make it more compact. So I'm gonna put these 2 buttons here. They do work. Always nice to press them. And we need to get power for both of these. So we need 2 resistors. There we go. So we have 1. Power him up. All right, next one in here. So button boss should be defeated. We have our input going on one side, which means this other line will be the output, and this guy has input coming this side, so this will be output. So what do we need next? We need to make an OR gate. All right, so we need yet another resistor. Really starting to use these a lot. So got this. Let's see, where do we put the OR gate? Let's say we put the OR gate over here. Okay, so we have our input for our OR gate. And the way we want this one to work, like before, is we want it so that when any one of these buttons are pressed, this guy's able to go home to a circuit. So we're going to need, I guess, 2 transistors. All right, there's 1, 2, facing me, EBC. We know that the collector will take power from the resistor. How come he doesn't want to go in? Okay. Maybe I can zoom in a bit. And we know that the other one, I'm going to put it side by side. I think we could probably share some pins between them, some rows, but I'm just going to put them side by side. So we have our 2 transistors. Did I say resistors before? I don't know. So 2 transistors. We know that we're going to have, so we have power in one. We're going to have our bases controlled by our buttons, and then the output needs to be grounded. So let's get a little, there we go. So now that's grounded. Power coming into collector A. Right now there's no way to get to collector B, but collector B, if you did get the power, then it emits to ground. So now what we need to do is connect these, which again, I think in an OR gate, they can be connected in all sorts of ways. At least in my mind, they can. So I'm just gonna connect their emitters. I think that makes sense. So emitters connect together. That way when one of them engages, they both share it, right? I think that makes sense. Okay. So if he emits, then he also emits. No, there's a problem here. All right, so if power comes up, we activate with the base, it goes out. This base is not activated, so it gets stuck. So we do need to connect the bases together. I mean, I think it will work. I don't know if it's the best way, but don't really even know what I did before on the last OR gate, but this should work. Right? So when we activate one base, the other base activates. Yeah, and they both emit. So they basically just share everything, which I don't know if that's an overkill or something, but so let's move on. So we know that our buttons need to tie into these. So let's get that going. So we're just sending this down here. So I guess this is B's output. Let's just send this down for the future. So we have B's output going down both ways. And we do need to put this LED in. I forgot about that. LED is going to be our output. So let's go get an LED. Long legs is positive. So this guy will just ground himself, I think. So he's our output. Now we need A to go into this guy. So we need to send his power down. So we'll say A's power is orange? Yeah, let me move this down. In. Right over here. All right, so we have button B, which sends power, his input. Oh, I think I put these on the wrong side, damn. Okay. I put them on the power side, not on the output side, the gray wires. So let's fix that. All right, this looks a little better. And now this guy's output goes down, and this guy's output goes down, this guy's output goes up, and then we need another for here. So let's connect these together and just make sure it works. I like to make sure everything works at each step. All right, so this is a maroon guy that will jump B's input to the B transistor of the OR gate. Okay, so we click him, and this base is energized. Now for A, let us do the same thing. So this is A's output. So we just need another maroon guy. All right. I think I zoomed in a little too much. So we have our resistor going to transistor A. When A is pressed, right, orange wire over into the base, he's energized, collector can emit. And whenever the base is activated here, it's also activated here. And he emits his power into this guy, who then, since the base is activated from either one of the buttons, since the bases are connected, he'll emit out to the LED. So I think we can plug this in and try it. We also have to connect our power here for our buttons. So, all right, so I'll just put them in anywhere here. And then I think that's it. Let me just do one last double check, make sure all positive power is resisted. All right, let's give it a shot. So we have positive, negativo. All right, that's an OR gate. That works, right? One or the other turns it on. It's a good start. Good start. So now let's do the not AND gate. And by the way, I could have used these cables and plugged into our existing gates, but I figured for practice, it's just better to rebuild them, especially since this is going to be its own gate. I don't want to compromise the other gates just to make the exclusive OR work. The key to me for anything that has not in it is it needs to be on by default. So I'm going to get another resistor. And all right, so then over here we can have our not AND gate. So we have power coming in, and really all we need is an LED to test this, right? We know this LED should be on by default. So 1 and 2. All right, so he's on. That's a good start. So all we need to do now is create a cheaper path to go home that will be activated when both of the buttons are pressed. So now we're essentially making like an AND type functionality. So we plug out power. We know that's the expensive way home, and now we need to make our cheap way home. So that's going to be a transistor, right? Transistor is going to pull power in parallel from that same point. Very thin. All right. So we have power coming out, but we need to put these in series, right? Because both buttons have to be pressed. So this guy's going to take power, but he can't make the circuit to go to ground unless both bases are activated. So he's going to emit directly into B. A is going to emit directly into B's collector. And then B's emitter will just go to ground. And then now what we need to do is connect our buttons. So I'll just use the orange. At least it's clear on who's who. So we can tidy it up later. So this will go into A's base. Okay. These orange guys never like to go in. Okay. So he goes in. He's already connected here. And then now B, who is on this gray cable, needs to go over here. All right, that works. I don't like all the colors. It's not color-coded at all. But let's see if it works. All right, so these guys are connected. So we have a resistor going to collector A, which outputs out the emitter when activated to collector B, which will, when activated by B's button, will go to ground, creating a cheap path to ground, skipping the LED, turning the LED off. If this path is not available, the LED will be on. So I think that properly satisfies our requirements for a not AND gate. Let's see if it works. I'm going to plug in my power. He's on by default, which is good. Okay, we have a problem. This is behaving more like a not OR gate. And I don't know why. And this guy, the OR gate, stopped illuminating. What the heck? If I take out one of these guys, what happens? Nothing happens? Okay, this guy works again. What is going on? Let's see. I don't know why the OR gate would stop working, to be honest. Because once power is flowing through the transistors, it should be a much cheaper way to not a much cheaper way. It's only one way to ground over here. This guy's on by default. Well, now they're totally separate circuits. I guess there's some sort of connection happening. Because when this guy's plugged in, the light is dimmer. Okay, so that LED is working right now. But when I put in this guy, it stops working. That's so weird. I'm pretty perplexed. And this guy becomes an OR gate, which is so weird because the only way for the power to skip the LED is to go through here. And both of these bases need to be activated for that to work. So for one button to be pressed, for A to have the base energized, it should get stuck in the collector of B and not be able to go out the emitter. So I don't know what's happening. The first thing to do is to get the meter and just see what's happening. Good thing we learned about getting voltage and current readings. So first, I'm a little confused as to why this guy will not power up, because this gate, basically anytime any power reaches any of these bases, this guy should be lit up. So let me take a look at that first. I'm going to try and take this reading of this LED. How do I do this and press the button? I do have these clips. Let me see. I do have these little clips to connect to little alligator dudes. Hello. Okay, this will connect to Mr. Terminal guy. I don't know what you call it, terminal. Okay, and black to black, black to black, black. Boom. All right. And then I'm going to take the other ends and carefully put them on. Okay. So those guys are hooked on. And let's turn this to voltage. All right, so we have a negative, pretty high negative number, 0.99. And if I press a button, then it goes to positive 0.8. As I recall, these should be 1.8 volts. So maybe what's happening is there's some kind of voltage leak or something like that that's preventing this guy from turning on. But the good thing is that he does receive voltage. And this guy, now it's 0.95. That's so weird. So he does receive voltage. Oh, I'm just noticing, did I pick up the wrong resistor? These look different. Oh man. Yeah, these look different. All right, so I have a couple issues here that I need to figure out. Let's take off these. Let me turn this off. Take out our resistor. I'm gonna hook on my little legs since I have them out already. And then let's check our resistance. So this is a 40 something ohm resistor. Wow. So there's a lot more current that was flowing there than I intended. So I have this other resistor that I had seen there. Maybe this is the one that I cut. Yeah. Okay. So this is 1,000 ohm. All right. So let's at least fix that problem. So I'll turn this off. I don't think this will really change anything, but if anything, I mean, it should have helped me with all that current. I'm going to plug in my power again and just see what happens. Just make sure. So our not AND gates light is on by default, as it should be. Press a button. So he's still behaving weird. So we know that this guy is receiving a positive voltage, the OR gate. So I'm going to skip worrying about that for now. We just don't have enough voltage maybe for this guy to turn on. I need to really figure that out because I've been using a lot of things arbitrarily. I use 3 volts, which I should probably show, but I can't show it without turning off my light. My setup is not the best. I've been using 3 volts just because I don't want to die, so it's the lowest possible that is available on my little multi-power source thing. And I'm using 1000 ohm resistors also kind of arbitrarily. So I guess I need to start really figuring out what I should be using to make this work. I'm also not sure. Well, there's an easy way actually to test that theory, because I could use another transistor as an amplifier to get this light turning on, I think. So I'm gonna get a transistor. I'm gonna cut my power. And what I'm gonna do is have another power source that is not a 47 ohm resistor. So let me take another one out. We can kind of see how far we're getting with all these resistors missing. It's really cool to see them being put to use. Okay. And what I'm going to do now is this guy's going to power a transistor whose emitter will go to the LED. Okay, and then it will just take the output from our OR gate into the base. So basically, instead of the OR gate itself powering the LED, it will power another transistor that has like fresh power, we could say. Our emitter from B will go to this transistor, hopefully turning on the light. It should. Because we have all this power now, right? Going to this transistor, this one resistor. And when our OR gate activates true, it should now go to this transistor instead of the LED directly and power it up so that he gets fresh power from this resistor. At least that's what I'm thinking. And 1, 2. All right, our not AND gate turns on as expected, but it's still behaving. Oh man, this does not turn on. The LED does not turn on. All right, let me connect these clips again. I need to be careful of that orange cable there. It's very close to making a problem for us, I think. Actually, no, I'm gonna, out of an abundance of caution, I'm gonna take this out and attach it on this side instead. I forgot this was zoomed in. Maybe you didn't even see that. So I'm gonna connect my meter again, and let's see our voltage. We still have a negative number, and if I press a button, I'm still getting 0.86. That's so weird. There's got to be something wrong with the circuit. I mean, obviously, but maybe my logic is wrong, and this is not the way it works. I was thinking that the buttons being in parallel could output to both. Maybe I'm missing something. Let's double check again. I am really at a loss for how one button is able to activate both of these, because there's no other way for it possibly to get ground. This is the only ground, other than of course LED, which is lit up now. But how is one button activating 2 gates? Like, what the heck? Because this guy, his power comes out, goes to A. His other power goes over here and goes to, oh yeah, over here. A's power does come out and goes here, but look at it bridged together. So that's the problem. Yeah, that's the problem. Because, so in this case, I guess the power can go backwards. I mean, who tells the power which direction to go in? I don't really know. But when I press one of these buttons, I guess it's going in here and lighting everybody up but then escaping back this way. But yeah, this is a problem. So my OR gate is messed up. Damn. My OR gate works by itself, but he doesn't play with other people, I guess. Well, there's a lot of ways to make an OR gate, I think. We can connect the buttons together, which is basically what we did here by accident. I didn't even mean to connect them together. I meant to connect the bases together. But I guess it's the same thing since they're both connected to their bases. All right, so when we plug out power, how do we solve this problem? So we need one button press to be able to activate both of these. Or maybe that's not the right way to phrase it. Really what we need is one button to make sure the power coming from this resistor ends up... Actually, I'm going to undo this then because let me not overcomplicate. So one problem at a time. Let's rip it all out. Okay, we'll just go back to ground, or output. So the question is, how do we make sure this resistor goes to this LED with one button press? We know we can't connect the bases because that will effectively connect our buttons, which will send weird signals over here. Because once one of these bases is activated, it seems that both of our buttons are getting power and going here. That's how this is working. Yeah, that's how this is working. So we're essentially just inverting. This is working as an inverter for this somehow. But let me focus on getting this working. So we know that the emitters should both connect. Maybe the collectors should both connect instead. Just one little move over might do it. Because now, if we activate button 1, emitter goes, which passes through this emitter. And if button 2 is pressed, then this should work. So we're basically treating this as one transistor because the collectors and both emitters are working. I think this works. Both collectors are always powered. That's the key. So any base activated, even though they're separate, should create a circuit here. Because the emitter, but the emitter and the base also share power now. I don't know. Let's plug this in and see. All right, our light's on. That's a good sign. Ooh. Okay. We're made progress. The light doesn't turn on. It turns on for one of them. That's so weird. But the good thing is that not and works. Both need to be pressed. So this is definitely progress. So our not and gate works, but our OR gate is not working properly. I think I should look up the specs for these transistors because I know nothing about them really to see how much voltage they need. Because we know that this voltage has dropped way down to 0.8 volts. Oh, before I was talking about the adapter. So if I cut my power to all the circuits, it will turn off this light too. I guess I could just take this out and show. So I'm going to cut the light. I'm going to turn off all the power. You can see the light went out. And if I slide this out, then you can see this is my power supply. And this is the light that I used to record. You know, this light right here. Is powered through the USB of the actual adapter that I use for the breadboard. So that's why I don't really have a good system here. But this is the power supply I'm using. And you can see it's 3, 4.55, 6, 7.59, and 12. I didn't even know there were so many. And I just used 3 because I don't want to die. So I'm using the safest one. But I need to really figure out if my voltage is right for this entire operation. So it's a good time to start learning about that stuff. Almost by necessity, I think, at this point. So we'll see how it goes. I'm going to try to find the docs, the data sheets, and then go from there. All right, so I'm going to look up the transistor, which is the 2N3904, and datasheet, I guess, is what we need. First one, I guess. So I don't really know exactly what I'm looking for. What I'm hoping to find out is just what voltage do I need to send into the base to ensure that it's activated. So there's a lot of stuff here that I don't understand just off the bat. There are some really high values here, 40 volts, 60 volts. I don't know what breakdown means, collector base breakdown. I assume this is volts DC. On characteristics, small signal characteristics, switching characteristics. Yeah, this has some very complicated things to it, like rise time, fall time. I have no idea what that really means. Yeah, this is all stuff that's pretty far over my head. I really kind of want to know something simple, I think, which is just, hey, what voltage are you expecting? All right. It must be in these charts. So on characteristics. Okay. Collector emitter saturation voltage, base emitter saturation voltage. This sounds like something. Really, the base is what I'm worried about. What is base emit? Let me use the suggestions from Google to also help me. So base emitter, yeah, saturation voltage. The voltage between the base and the emitter terminals of a transistor that ensures the collector junction is forward biased. What does forward biased mean? The base emitter voltage can go above 0.7 volts when a transistor is in saturation, at which the transistor saturates. What is transistor saturation? Saturation is the on mode of a transistor. Okay. All right. So the base emitter, we can call it energizing voltage, I guess, to energize the to turn it on. I think this is what I need, and the minimum is 0.65 volts, which this makes sense to me, I think. Yeah. So I'm gonna print this and then go from there. I'm gonna test. Well, I don't know if I'm gonna test this out right now, but what I'm thinking is that we know that the LED in the OR gate does not turn on, but the NOT AND gate is working fine. So maybe what we should do is output both of those values to our final AND gate and just see if it works, the exclusive OR. So maybe I'll make a new AND gate, or I'll just, which is a plan, until we got diverted by this problem, or I can put it into our old AND gate using some cables and see what happens. But I feel like, I guess it's a voltage problem. It seems like that to me, because once we saw that the LED from the OR gate was not pulling the 1.8 volts, I guess there's just not enough, even though when we used the transistor as anyway, I think I should probably go back to the breadboard so that what I'm saying is not just my voice. There's some illustration. So I'm going to print this and then take it over there. So the on characteristics, the one that stood out to me, or that I was looking for, was really this one right here, 0.65. I think that suggests that what we need is 0.65 volts going into any one of these bases to, as they call it, saturate it, or as I call it, I guess, energize it, to allow the collector to output to the emitter. And we have over that value, so I don't think that's the problem. I'm assuming these buttons can output parallel, two different places at once. Very similar to how this power is giving off this power and even this power, which goes to these two. So we have parallel connections from our VCC, as they call it. I don't know what VCC stands for, but the power source. Why doesn't the button do that? Why not send it in both directions? So I don't know. That's a good question. I'm always thinking about voltage. Maybe it's current, because voltage splits in series, as we saw with our experiments earlier. In the beginning with the two resistors, when it was one resistor, then the sole resistor got all the voltage. When we added two resistors, and it was split evenly. I'm looking for that paper right now. I know we have it somewhere. Well, I could do a new one. So we know that in a series, if we have, in my case, 3 volts, and it's, let's say this is the 3 volt line, and we connect to our, let's say, resistor, which is like this, I think. Let me see. I guess there should be more lines in it. Oh, wait. Oh, this one. Okay. So we have a resistor, and then let's say we have another resistor, and then we go to ground. Let's say this is a ground, G and D. In this case, assuming these are the same, this guy will get 1.5 volts, and this guy will get 1.5 volts. That's what we saw from our test, and that's what Leonardo said would happen. Now, I'm completely forgetting to think about the inverse of this concept, which is in parallel. So this is series. In parallel, let's say we have another 3V circuit, right? And we have two connections. And let's say they're both going to resistors and then to ground. Both of these will be 3 volts, but the current will be split. So I'm going to write, this is parallel, and this is series. So in this case, let's say my thing, I think I had a 2 amp max. But the power source doesn't push amps through a circuit. The circuits pull it based on their resistance. So if this is a 1K and this is a 1K, then we know that we're going to have 3 milliamps coming through here, through each one. We can consider this a VCC, and then it goes to 2 different circuits. So if we use this logic, and we know from before that when we take out this, if we take out this wire, I think it works, right? Because the current, I guess, only has one way to go, which I didn't think about when it was jumpered together. I didn't really continue that thought, like jumping these together, what did it really do? Well, it opened the circuit to come this way. I don't know. There's probably more in here too that I need to look at. They do have a little chart here. Hey, these guys use a 3 volt source too. I thought 5 was like the standard, but these have 3 as well, so I'm not going to worry about my voltage. And these have 10K resistors going into their base. Damn. Maybe I'm doing something wrong with that. I've always thought that once I resist the power coming into my buttons, I don't need to worry anymore. But if these are in parallel, then maybe I need to have more resistors within my circuit. And this point would seem to be the place. That might be what's happening. That's probably what's happening. I'm pretty sure my logic is good. I think my setup is pretty good. I think this button then, we know we have a leak, because as soon as this is pressed, both of these should turn on, allowing current to go. Well, this button is clearly the problem, and it always has been. This button always faces an LED on his path, or he faces some kind of block. In this direction, he goes to collector A, which gets stuck at collector B unless collector B is pressed, forcing it to go this way, which will activate all these LED, all the transistors, and escape out of the LED. So that's why he works. He has no alternative. This guy actually does have an alternative. With our resistor, our inverter, if we take this guy off, then the current is always flowing through the LED until we give it a cheap way to ground. In this case, that must be what's happening. This guy always has a cheap way to ground. Yeah. Oh wait, look at this guy trying to come over here. Little poser. Go, go. Yeah, that's what's happening. This guy has a cheap way to ground. Look at that. straight into the base, out of the emitter. Super cheap. Over here, he's got a mountain to scale, right? Using the same analogy as before. He goes into the base, which activates it, but he has to go out the LED. So we're basically facing an inverter situation here. That's exactly what's happening, except this guy isn't lit by default. But we're still diverting the energy away. So if we added an LED right here, then it should face a similar obstacle and maybe send in both directions. I'm gonna try that. Okay. So this button is still connected here, but it's going now through an LED to hopefully balance it out, is what I'm thinking. Yeah. This works. Look at that. This works. So it's a resistance issue. So either button activates our OR, and both, and they leave this guy on, and both turn off our not AND gate. So this would be a, if we combine these together, we get a 0, which is how it should be, right? Because exclusive OR, both of them are pressed right now. So we should get a 0. 1 is pressed, we should get a 1. 1 and 1 make 1. So let's add our AND gate. Man, I should have noticed this before, that this is a cheap way to ground. But this is definitely something that I won't forget. When I have parallel connections to like a button, then we need to make sure, I guess, that the resistance is split. So what I'm gonna do is I'm gonna plug up power. Now I'm excited again. And I'm gonna add a resistor here instead. Okay, so that's a 1K. Hey, it's not working. Maybe he's not enough. The LED is what resistance? I don't even know what it is. I'm getting a 1. That means it's more than 2000. Wow. Is it safe to take a resistance reading? It was illuminating. I'm not going to take it. I'm a little worried that I'm going to run too much power through it or something. But clearly it's more than 2000. So this is our 1K. We could use it for our AND gate, actually, which we have to build. So let me put this in right over here. The example from this thing has 10Ks going into the buttons. So maybe I'll just put a 10K. And the LEDs seem to be 10K. So I have some 10Ks somewhere around here. But yeah, that was the last 1K resistor from that pack. Kind of cool to see all of them being put to use. All right, so we have our 10Ks here. I'm going to take one out, cut him. Put his little legs away. And I'm gonna put this guy, hey, I think I bent it when I was cutting it. Put him, okay, in there. Let's see if this works now. More resistance. All right, so we have our light on, good sign, on, and on. Hey, wonderful. All right, so we got a working OR gate and not AND gate from one input. Man, I never thought it would be that hard to get this going. I thought it would have just been super easy to have the output, but really, so resistance does matter. Newsflash. So yeah, this is good. This is great. So now what we can do is we can build our AND gate. I'm going to make a simple one, and we can hopefully integrate, right? Output, and then our AND only turns on, which will complete our exclusive OR output. So let's knock that out real quick and try and make up for some lost time. So we are going to have an LED, which gets our resistor. Our resistor goes into LED, and then it goes into two transistors in series. All right. So we have our LED going into transistor A's collector, which goes into transistor B's collector, and then needs to go to ground. So by default, this guy's getting energy, but he can't go home. When we activate both these transistors, it should go home. Very simple AND gate that we did as one of the first gates before we flipped it around and all that. So this is just an indicator, which is perfect for our exclusive OR. And now I guess all we need to do is take the output from these LEDs. So I'm going to flip this one around so we can easily access the output. Because remember, these LEDs are the output itself. And I'm going to get two cables. I'm going to say blue is A. So this goes in. Green is B. This goes in. And then we're going to interface now, connecting all of our gates together, the 3 gates together. All right. Well, let's turn on power, see what happens. Oh man, nothing happens. Okay, so we have one switch to turn on 3 lights. Wonderful. Clearly what's happening here is the same as before. And this is the great thing about learning and having similar problems. So when we had these buttons connected, if you remember, these buttons would work to turn on this guy because he was getting power to both of these transistors through both buttons since they were joined up here. So pressing one button would just join everybody up. These would light up, this would light up, these would light up, making both of these light up, making both this light up, even though only one button was being pressed. Everything was lighting up. Obviously, that's what's happening here. These cables are super connected together. Sorry, the cable's in your face. So there's just way too much current flowing everywhere. I was so focused on voltage before. It's a current and it's a resistance. So what we need to do is add more resistors to the inputs of these bases, similar to what they have in the documents. So I'm just going to keep using 10Ks then from now on for my inputs to the bases and see if that fixes it. So let's see if the lessons we have learned make this a very short issue or if there's something more serious going on. But we know that they work. So it's just limiting where the current can go. Okay, so let's just kick this guy to the side here. And we'll create a new input for this guy. And now we can plug it in again, I think. So our output for B goes into our resistor, and our output for A goes into our resistor. All right, let's plug them in. That looks great. That looks great. Hey, now our LEDs are now failing. I don't really care about that. I guess it's a current thing or voltage. It's probably the voltage being split between this resistor and this LED. But I don't really care about that. Really, we could. I wonder what's cleaner. Maybe we could replace the LED with our resistors. Because we kind of have doubled up resistors. So I should probably do that. So let's plug out power real quick. Plug out these guys. Or these could just be plugged in straight into the inputs. Yeah, that makes more sense. Don't need the LEDs anymore. Right? Yeah, let's try this. Okay, so A pressed, B not pressed, B pressed, A not pressed. We have an on light. Both on, we have an off light. And both off, we have an off light. Perfect. We have our exclusive OR gate. So we have all of our wonderful gates now, which it's a lot. But now we can hopefully mix and match them together and see if I can get them all. What I'm going to do next is try and, I'm going to take a little break and I'm going to try and draw all of these as a schematic to start getting a bit better at that, and then see what we build with our gates. So cool, thanks for helping. And it's funny how this kind of solution was found. You know, I was looking for voltage for the transistors. Move this over here, but this was never an issue. And this really is what kind of helped point it out, along with the problem that we had before, just kind of revisiting it. Anyway, I will get started on some schematics.